you for the introduction. Today I will talk about the neutron diffraction and synchrotron X-ray diffraction and their synergy in the studying of the building processes in the nickel superalloy. So just a few key points from the laser power bed fusion. You have many processing parameters that influence the microstructure. And you can use these different parameters to tailor the microstructure or even create like a complex microstructure within one sample. Also, with the laser power bed fusion, you impose quite high residual stresses in the sample. So you need to do some post-treatment. But when you do the post-treatment, then you, on one side, decrease residual stresses, but also you can see some changes in the microstructure. And the traditional two-step annealing that's done at the temperatures over 1000 degrees cause that you break this microstructure created by the additive manufacturing. So our goal is to find out if we can optimize the post-treatment and also maintain the tailored microstructure and achieve high performance. For the characterization of the samples, beside the traditional microscopy, we used the neutron diffraction. First characterization was done at the Paul D beamline at SynQ Paul Scherrer Institute. It's time-of-flight diffractometer, and it has the one detector bank at 90 degrees to the incident beam. This is okay for the characterization, but for the in-situ experiments, we had to go to the Engine X beamline because they have two detector banks that can collect the data simultaneously. And later on, you will find out why this is the key parameter for our study. As I said, we also did the synchrotron X-ray diffraction that was also at the Paul Scherrer Institute at MS beamline. For this, we use the 2D Pilatus detector, so again, we can get the complex information about the sample. Just a few words about the neutron diffraction. So it's the reflection of the neutron beam on the lattice planes, and if we say it very simple, it measures the distances between the atoms. Now, here you have the display the Bragg's law, and from that you get the diffraction peaks on the as your result. And if you have detector banks, you can collect the data from two different directions of the sample. How do we evaluate the residual stresses with this? When you have an unstrained sample, say the lattice is cubic, you see that it's cubic, so both sides have the same length. Therefore, you get overlapping peak from both directions. But the moment the residual stresses or any kind of stresses are imposed, you no longer have the perfect cube or square, but it gets prolonged in one direction and shorter in the other. And that causes splitting of the diffraction peak. And what we basically measure is just this splitting of the peaks. Why we use both neutron diffraction and synchrotron X-ray diffraction? Neutron diffraction has high penetration into the bulk of the material, so we can really study the inside of the samples. We can penetrate several millimeters, so we do not release the residual stresses just by thinning the sample. We have a relatively high gauge volume, so we get good statistics. But on the other hand, we have low spatial resolution. With X-ray diffraction, we have to use small samples. Also, the spot size is much lower, so we have high spatial resolution. but there is also a problem with the low statistics. What you can also see that X-ray diffraction has much higher data to background ratio. So here we can even see the peaks from the precipitates, which are with the neutron diffraction just hidden in the background. We used Ni Alloy718 for our study, which is precipitation hardenable alloy. Our alloy contains gamma double prime precipitates, no gamma primes, and also we were able to observe with the synchrotron the delta phase or carbides or laves phase. We used this simple geometry of the samples, and we created two different scanning strategies. Why we choose, like, let's say, this kind of weird strategy is that we tried to achieve the symmetrical stresses in the center, because to evaluate the complete stresses, we need 3 components, but we have only 2 banks for the neutron diffraction. So with this, maybe we can get cylindrical symmetry in the center, and we can measure just those 2 components. Just initial microstructure from the X-ray diffraction, we can observe the gamma peaks with quite significant shoulder on the right side. That shoulder is coming from the gamma double prime. We can also observe the laves phase here. If we, when we did the scan through the concentric sample, we can observe that there is higher gamma double prime phase fraction in the center than at the edges, which is due to the, let's say, higher heat input in the center due to the lower, smaller radius of the concentric scanning pattern. Yeah, now this is the results from the characterization of the samples from all the beamline, and we can see that the actual direction and the radial direction in the center, they have very high splitting. Therefore, we can observe that we have quite high residual stresses there. And what's important is that the radial and the hoop direction have the same value there. Therefore, our theory that we will have cylindrical residual stresses got confirmed, and now we can perform the experiment with just 2 detector banks. We also evaluated the residual stresses and more wood microstructure. That would be completely other talk, but we can discuss after the coffee break, or you can have a look at our latest paper. As I said, we went for the in-situ experiment to engine X beamline, and there we heated up the samples with 40 degrees per minute, always 2 minutes heating and 2 minutes holding the temperature to kind of balance the temperature. And then we repeated the very same procedure at the MS beamline. And you see the experiment is quite simple. You just follow the evolution of the despacing. You can see from the beginning the increase, that's just the thermal expansion. And if you plot just the difference between the axial and the radial bank, you see that at the beginning this is constant, and the moment you got above 500 degrees, you see that this difference is starting to decrease. That kind of means that we have the reduction of the residual stresses, then we stabilize at 800 degrees, keep following this progress, and we can measure when the data from the 2 banks start overlap again, and at that point we have again stress-free sample. Again, same experiment repeated at synchrotron, and we can observe that with the increasing time, we have some increase of the shoulder, also a bit change of the peak. Also, we observe that there is there is increase of the delta phase. So here we can compare the two samples. As I mentioned before, the concentric sample had much higher residual stresses in the center, which is again here as observed as the higher difference at the beginning. We can see that after 2 hours of annealing, the alternate sample got some saturation. For the concentric samples, we needed a bit longer time, and as I already described before, we see increasing volume of the gamma double prime, but also appearance of the delta phase after 1 hour. We did also the measurement of the samples after annealing, the full characterization, and we can observe that the residual stresses were almost completely annealed. We did these measurements at a different temperature. For example, at 1000 degrees, you can see that the residual stresses decrease immediately when we reach the 1000 degrees, but we get much higher volume fraction of the delta phase. Also, what's possible to notice is that the annealed sample has a different lattice parameter for the gamma matrix. This is again caused by the difference in the precipitation after the annealing. We did also quite a rapid test. Unfortunately, you have to align the samples, so you cannot just measure how is it when you put the sample directly in 1000 degrees. You still have to ramp it up somehow. But again, we were able to observe that immediately when we reached 1000, after 10 minutes, the residual stresses were fully annealed. We also tried lower temperatures. Here we can observe that the microstructure is kind of stable, that you do not see any precipitation of the delta phase, no increase in the Lavis phase, but also you need much longer time to anneal the residual stresses. We also were interested about how is it with the mechanical properties. Like if we do the annealing, do we maintain the good mechanical properties or even improve? And we actually can see that we did also the conventional annealing, which is 2 hours at 1100, followed by 8 hours at 700 and 10 hours by 600. And we were able to achieve a higher yield stress by annealing the samples just at 700 degrees for 6 hours. This is because we preserve the microstructure, the unique SLM low anneal boundaries, and cell structure. So I would like to summarize my talk. We are able to in situ observe the annealing of the residual stresses and change of the microstructure. We can observe that already the conventional annealing is good enough to release all the residual stresses. But if we do the annealing at lower temperatures, we can achieve even higher yield stress for this kind of material. Thank you for your attention.